Secure Sockets Layer Protocol, or SSL, was standardized by IETF, and it is known as the Transport Layer Security, or TLS. This is the principal means of securing communication between an internet client, that is a browser, and a server. SSL is comprised of two main protocols, the Handshake protocol and the Record Layer protocol. The Handshake protocol is used to negotiate the set of algorithms to be used for securing the communication link. That is, what are the algorithms that are going to be used for encryption, for hash computation, and the method for key exchange. Okay. Then it does server authentication. Okay. Thirdly, the Handshake protocol is responsible for deriving the keys. Okay, the encryption key, which is used for encryption, the authentication key, which will be used for the MAC computation. Next, we have the Record Layer protocol, which actually does the job of providing message authentication, integrity checking, and encryption. In the Handshake protocol, which algorithm is to be used and what the keys are, those are being derived. Whereas the actual job of message authentication, that is computation of the MAC, the encryption, etc., is done by the Record Layer protocol. The Record Layer protocol sits just below the Handshake layer. That is what we have already seen. Okay, we have the application layer and we have the TCP. These two layers together is what forms the SSL. So the SSL is made of the SSL Handshake and the SSL Record Layer protocol. Okay. Now the Record Layer protocol protects each message exchanged by the two communicating parties. It detects replayed, reordered, and duplicate packets. So if any attacker is trying to get into the system using a replayed packet or a reordered packet, then the Record Layer protocol will be able to detect, and the process of establishing the communication between the client and the server will be aborted. So first we will see the Handshake protocol. Okay, the client initiates the handshake with the server. Okay, so whenever you interact, it is the browser which will initiate the handshake with the server. So yeah, when the client initiates, there are three possibilities. One, you may start a new session. It is for the first time that the client is trying to communicate with the server. Or we may try to resume an existing session. Okay, already a session has gone on for some time. Okay, you have not messaged for some time. Okay, after that you are again sending a message. Or you may establish a new connection. Okay, you may not want, it is always not advisable to have the same key between the client and the server, because any attacker may be able to get hold of the key. Okay, so for this, by sniffing into the packets. So it is always better that you keep changing the keys. Okay, we go to establish a new connection in this case. Okay, so within the session, we are not going to change the session. Within the session, we will establish a new connection. So any one of these three may be done by the client. The handshake with the server will be required for any one of these three conditions. Now there are four main steps in the SSL handshake. Okay, to establish a new session. Okay, the first one is agreement on a common cipher suit. That is, what is the algorithm that we are going to use. Receipt and validation of the server certificate by the client. Communication of a premaster secret and computation of derived secrets. integrity verification of handshake messages and server authentication. So first we see step 1. Two messages are communicated in this step. Okay. The client is the one which is going to initiate the handshake. So the client sends the client hello message and the server responds with the server hello message. Okay, now what is this client hello message? Okay, here the client will send the session ID to the server. Suppose the client is requesting for a new session. Okay, it wants to start a new session. Then the client will send the session ID as 0. Okay, otherwise it will send the session ID, the ID of the session, which it wants to be renewed. Okay, so the server on receiving the client hello message reads the session ID. If the session ID is 0, then the server knows that the client is requesting a new session. If it is not 0, the server knows that the client is requesting for renewal of a existing session, that is whose session ID is given in the client hello message. Okay, now on the, the server will now have to take some decisions. Okay, what are the decisions? First, it has to find out if a new session is to be established or an existing one is to be renewed. This is done looking into the session ID. Next, the algorithm to be used in computing the MAC for message integrity is to be decided. Okay, now here in SSL, we use either MD5 or SHA-1. Okay, so the algorithm what SSL allows is MD5 or it can be SHA-1. We have studied about these when we studied the cryptographic hash. MD5 standing for message digest 5 and SHA-1 standing for secure hash algorithm. Okay, next it has to decide whether or not message confidentiality is required. Okay, if message confidentiality is required, then what is the encryption algorithm that we are going to use? Okay, the encryption algorithm could be DES, it could be triple DES, it could be AES or RC4. Okay, also it should decide on what the key length should be. Okay, so it decides on the algorithm that is to be used for message authentication. It decides on the message confidentiality, the algorithm and the key length. Okay, now the next, it has to also decide on what the key exchange method is. Okay, like in IKE we have seen how Diffie-Hellman is used for key exchange. Okay, here in SSL different key exchange methods are allowed. Diffie-Hellman is allowed. Then RSA is allowed. Okay, many key exchange methods are allowed. So the server has to decide on what the key exchange method would be. Okay, this key exchange will be used to communicate the pre-master secret. We will just now see what a pre-master secret is. Okay, in addition to this, in the client hello message, it will also send a nonce RA. Okay, this is to ensure the freshness of the message. Okay, so the server will reply to this nonce RA in the server hello message, and also it will generate another 32-byte nonce RB. Okay, to ensure again the freshness of the message from the server to the client. Okay, so this is what happens in step 1. Step 1 consists of 2 messages, client hello and server hello. Client hello gives the session ID. Okay, server hello, it will decide on the algorithm to be used for message integrity, for message confidentiality, that is the encryption algorithm, then the key exchange method. Okay, and in both the nonces are being exchanged. Moving on to step 2. Step 2 The server communicates its certificate to the client. What is the certificate? The public key, what the server has, that has to be communicated to the client. Okay. The server will be encrypting using the client will be encrypting using the public key, and the server will be uh, uh, sending the its public key to the client for verification. Okay. On as soon as this public, how is this public key sent? That is through the digital certificate. That is what we said, certificate. Okay. Now, as soon as this digital certificate is received by the client, it has to, first of all, we have studied, it has to verify the the authenticity of the certificate. Okay, so it checks the owner's name, that is the URL, whether it belongs to the same URL or not. It checks the validity period. Okay, now we have seen already when we study digital certificates, there are the validity period is also given in the digital certificate. So if the certificate is valid, only then it can be used. Also, you have the signature of the certification authority in the digital certificate. Okay, so that is also verified. Okay, after successful verification of these fields, okay, we only know that we have guaranteed that it is from a server, but we are not authenticating the server. Okay, because this certificate can also be sent by any attacker. Okay, since it is all in the clear, we are not using any encryption, it can be sent by anyone. Okay, so we are not sure that it is actually coming from the server, but we only know that the certificate is an authentic certificate. Okay, the authentication of the server is done only at the end of step 4. Okay, so that is step 2. Next, we move on to step 3. Okay, in step 3, the client chooses a premaster secret. Okay, what is a premaster secret? That is a 48 byte random number. A 48 byte random number is selected by the client. This random number is encrypted with the server's public key. Okay, it is encrypted with the server's public key and sent to the server in the client key exchange messages. Okay, so the premaster secret is encrypted using the public key. Public key it has obtained in the previous step in the certificate that it has received from the server. So it will encrypt and it sends the message to the server. Okay, thereafter, both client and the server compute the master secret. From this pre-master secret, both the client and the server independently calculate the master secret. What is master secret? That is a HMAC style function. Okay, which takes in as arguments the pre-master secret, the two nonces RA, RB. These have been exchanged in the step 1 and some predefined constants. Okay, so using all these, that is the pre-master secret, the nonces and the constants, a master secret is computed. Okay, again using either the cryptographic hash function SHA-1 or MD5. Okay, so now both of them independently have got the master secret. Next, they go on to calculate 6 derived secrets. Okay, again, these derived secrets are HMAC style functions of the master secret, the two nonces, and different predefined constants. Okay, now why do we use these derived secrets? Okay, what are these derived secrets? One of the derived secret is the initialization vector that is used for encrypting messages from client to the server. So later on, when the data is to be sent, we will be using an initialization vector. Okay, so first we calculate the initialization vector that is going to be used by the client whenever it wants to send messages to the server. Okay, next the initialization vector for encrypting messages from the server to the client. That is also calculated. Next, the secret key for encrypting messages from the client to the server. Okay, so what is the key that the client is going to use? That is computed. Next, the secret key for encrypting messages from the server to the client. Whenever the server has to send a message to the client for encryption, what is the key that will be used? Next, the secret for computing keyed hash on messages from the client to the server. That is what we call as the client MAC secret. And the sixth one is the secret for computing keyed hash on messages from server to client. That is the server MAC secret. So the master key is computed. From the master key, these 6 derived secrets are computed. This is what forms step 3. Okay. Next, step 4. Okay. Now, the keys have been exchanged. Okay. Now, this step 4 is done, can be initiated either by the client or by the server. Okay. Any one of them can do it. Okay. In our figure, we assume that the client is initiating this step 4. Okay. So, the client will send the change cipher spec. Okay, now what is this change cipher spec? Once this change cipher spec message is sent, it means that this client is going to use whatever algorithms have been decided in the previous step, and whatever keys have been calculated in step 3. Okay, so whatever the client and the server have decided on, the algorithms, that is the algorithms for MAC, that is message integrity, for encryption. Okay, those are what will be used for in the following messages. Also, yeah, so this is what is meant by this change cipher spec message. Okay, now once that is sent, the client also sends the finished message. Okay, in the finished message, a keyed hash is sent. Okay, that is a hash of all the previous messages, whatever it has sent. That is the client hello it has sent. It has sent the client key exchange. It has sent the change cipher spec message. Okay, so all these messages, it takes a concatenation of all these and calculates the keyed hash plus a predefined constant. Okay, all the previous messages plus a predefined constant is taken. A hash of all these messages is taken, and that is also sent in the finished message. Okay, so the keyed hash serves as an integrity check on the previous handshake messages. Okay, what we see is all these previous messages, whatever we are sending, we are not encrypting. It is sent in the clear. That means as it is sent. So any attacker can always get hold of these messages. Okay, he can either sniff into them, means he's just reading and sending them back, or he can make some changes in the message and he can send it. Okay, now in case he makes any changes, then this hash, what is being calculated by the client, will not tally with what the server is going to calculate. Okay, the server has got, the client has meant some message here. Okay, it has calculated the key and it has sent, whereas the attacker has made change. So when it reaches the server, it will be a different message. Now, the server on receiving the finished message will go to calculate the hash. How does it calculate the hash? It will take the messages that it has received from the client, that is client hello, client key exchange, change cipher spec, and it will calculate the hash. If both are exactly the same, both the MAC that has been sent by the client, whatever it has calculated, and the MAC that the server is getting now by this calculation will both be the same. Okay, if both are same, fine. Otherwise, the server knows that an attacker has made some changes and it will go to abort the message. Okay, so the keyed hash serves as an integrity check on the previous handshake messages. So now, once the server receives the change cipherspec message and the finished messages, it verifies the computation of the keyed hash. Okay. Once it is satisfied, it will go to compute its own keyed hash. Okay. Now, what is this keyed hash? Okay. Now, this keyed hash, it takes all the previous messages that it has sent. What are the messages that the server has sent? It has sent the server hello message. It has sent the server certificate. Okay. So it takes these messages. It concatenates these messages. It takes a predefined constant. Okay. Again, this constant is different from the constant that was used by the client. Okay. So it takes a hash of these messages plus the constant, and that forms its keyed hash. Okay, and that is sent to the client, and it sends the finished message. Okay, now on the client, on receiving this, it will go to verify the keyed hash. How does it verify? It has already received the server hello message, it has received the server certificate message, and it knows the predefined constant. Okay, so it concatenates these messages, uses this predefined constant, and calculates the keyed hash. If that keyed hash and the keyed hash that it has received in this message from the server are both the same, it authenticates the server and further communication takes place. In case both don't match, then the communication is aborted. Okay. The client authentication. So this is server authentication. Client authentication as part of SSL handshake is optional. Okay. If the server or the client wants, they can go in for it. Otherwise, they need not go. So what is compulsory is all these 4 steps. That is, only the server authentication is compulsory. Client authentication is optional. It is left to the client and the server. Next, we see the key exchange methods. Okay, we have seen in step 2 that the server certificate is being sent by the server to the client, and that is being encrypted in step 3. The client is going to use this key that is received in step 2 for encryption. So how are these keys being exchanged? So the server certificate may be a signature only certificate. What do you mean by signature only certificate? Okay, that key, the public key that is there in the certificate may be used only for signature. Okay, if that is the case, then it cannot use it for encrypting the key. That is a premaster secret. The client will not be able to use this particular key for encrypting the pre-master certificate in step 3. Okay, so what should you do? The SSL permits the server to create a temporary public key private key pair. Okay, since the key in the server certificate cannot be used for encryption, now the server creates a temporary public key private key pair. Okay, the private key it keeps with itself. The public key, including the modulus, whatever parameters are required, and is signed by the private key that is there in the certificate. Okay, whatever private key it originally has, with that it signs this temporary public key that it has generated, and it sends that to the client. Okay, the signed public key and the certificate are communicated by the server to the client. Okay, now the client verifies the public key. Okay, from the server certificate, it gets the public key, it verifies this signature. Okay, and from this, it will be able to decrypt the public key. Okay, that is the temporary public key, and the temporary public key will be used to encrypt the premaster secret, and that will be sent to the server in step 3. Okay, the server now, since it has the temporary private key, it will be able to decrypt this premaster secret and get the premaster secret. Okay, so if the server certificate is signature only certificate, then the server is going to create a temporary public key private key pair. Okay, and that is what is going to be used for encryption by the client. Okay, the public key that is there in the signature only certificate will be used only to authenticate the public key. Okay, next, what are the key exchange methods that are used? As I said before, SSL offers a rich set of options for key exchange. That is, it allows you to use RSA-based key exchange methods, Diffie-Hellman key exchange methods, etc. Okay, so we will see two methods. One is the fixed Diffie-Hellman key exchange. Okay, now what is this fixed Diffie-Hellman key exchange method that is being used in SSL? Okay, assume that the server has got the certificate. Okay, the certificate contains the Diffie-Hellman parameters. What are the Diffie-Hellman parameters? You need the prime number, that is P. You need the generator, that is G. Okay, now the server, it has also got a public key, that is the A, which is the public key, is the A, which is the private key to the server, is known. Okay, now the G to the power of A mod P is the public key. Okay, so the certificate contains P, G, and G to the power of A mod P. This is sent from the server to the client. Okay, now in step 2, when the certificate is received, now the client knows the P, G, and G to the power of A mod P of the server. Now the server, the client chooses a random number B. Okay, it computes G to the power of B mod P, and it will send G to the power of B mod P to the server. Okay, now what does the client do? It has got G to the power of A mod P. Now it has calculated G to the power of A mod P. Okay, so it will do G to the power of A mod P to the power of B. Okay, and it will get G to the power of AB mod P. Okay, what does the server do? Server has got now from the client G to the power of B mod P. It has got its private key A. So it will calculate G to the power of B mod P to the power of A mod P. So that is nothing but G to the power of AB mod P. So both the A and B have got the value G to the power of A, B mod P, which is the pre-master secret. Okay, so both the client and the server have the pre-master certificate, pre-master secret. From this, they go to calculate the master secret and the derived certificates. So this is fixed Diffie-Hellman key exchange. Okay, the values for P, G, and A are fixed. Okay, now you have a second Diffie-Hellman key exchange method that is possible with the SSL. That is the ephemeral Diffie-Hellman key exchange. What do you mean by ephemeral? Ephemeral means temporary. Okay, so only for that particular session, this key will be used. The server generates the Diffie-Hellman parameters. Okay, now it has got a signature only certificate. Okay, that is not having the Diffie-Hellman parameters here. Okay, so the server is now generating the Diffie-Hellman parameters. Okay, that is P, G, and G to the power A. Okay, from A it calculates G to the power of A mod P. Now all these three will be signed using the signature only certificate that the server has. Okay, now it has signed, and this signature is what will be sent to the client. Okay, so, now P, G, G to the power of A mod P is all sent. Now the client receives this message. Okay, it first verifies the signature. Once the verification of the signature is complete, it will take the parameters P, G, G to the power of A mod P from this, and then it will go to select a B. It will calculate G to the power of AB mod P. That is the usual Diffie-Hellman key exchange process. And it will send G to the power of B mod P to the server. The server again calculates G to the power of AB mod P, and that becomes the pre-master secret. Okay, so what is the difference between the fixed Diffie-Hellman key exchange method and the ephemeral key Diffie-Hellman key exchange method? In the fixed Diffie-Hellman key exchange method, the Diffie-Hellman key exchange parameters are all present in the certificate. Okay, whereas in the ephemeral Diffie-Hellman key exchange, the certificate is only a signature only certificate. These parameters are generated by the server. Okay, so that is the difference. So you can have any method for the key exchange method. Server authentication we have already seen. Okay, the MAC is the one which is used. So all the previous messages are not encrypted, whereas it is only at the finished stage that all the previous messages together are included in the calculation of the MAC. Okay, the client will use the server MAC secret for checking the MAC that has been received by the server. The server will use the server MAC secret in order to generate the MAC. The client will use the client MAC secret to generate its MAC. Okay, so since these secrets are known only by the client and the server, if the MAC is verified, we know that this message has come from this particular client only or from the particular server only. So after the MAC is verified, the client is convinced that he is talking to the authentic server. Okay, next we see sessions and connections. Okay, we have seen already that it is better not to use the same key throughout the long session. Okay, if the session is long, it's better you use another set of keys. Okay, now in this SSL, okay, in all these steps, okay, which is the most time consuming process? Okay, the most time consuming process is this step. Okay, what is this client key exchange? The pre-master, that is the step 3. Okay, what is the step? We are sending the client chooses a pre-master secret, encrypts it and sends it to the server. Okay, this encryption is by the server's public key. Okay, this encryption is the most time consuming process in all these. All the other previous messages are only being sent in the clear. Only this is encrypted, and so it takes time. Okay, so we will try to avoid this as much as possible. When we go to change the secret key, okay, that is the secrets that are used between the client and the server, we will maintain the same pre-master secret. Okay, now you see that the master secret is calculated as a HMAC function of pre-master secret, the nonces RA, and some constants. Okay, so now here what we will do is we will maintain the same pre-master secret. Okay, the client and the server will exchange fresh nonces RA and RB, and they will be used in the new connection. Okay, the session remains the same, session ID remains the same, pre-master secret remains the same. Only thing is these nonces RA, RB will be changed. Okay, so for the new connection now, since RA and RB are changed, the master secret will be changed. Okay, since the master secret is changed, all the derived secrets will be changed. So you get a fresh connection with the same pre-master secret, but a new master secret and new derived secrets. Okay, so they will be used for further communication. Now, what is a session and what is a client? The session is what you are initially establishing between the client and the server. Okay, that it is initiated by the client. This includes the pre-master secret, the negotiated cipher suit, that is, what are the algorithms you are going to use for the message authentication, for message integrity, that is for encryption and MAC, and what is the session ID. This forms the session state. The state of a connection is, for the particular connection, it includes the two nonces which are different. The master secret is different because the nonces are different, the derived keys are different, and the message sequence. Okay, a message sequence is used, number is used to keep track of the messages. Okay, the order in which the messages are being sent, and which message is being sent by the client and the server. Okay, the client maintains a message sequence number, the server also maintains another message sequence number. Okay, so these two together are also used in the to establish the state of a connection. Okay, so you have a session state, you have a connection state. Yeah, so this completes our handshake protocol. So next we see the SSL Record Layer protocol. Okay, that is used to securely transmit data using the negotiated cipher suit and the keys derived during the SSL handshake. Okay, its main tasks are computation of the per message MAC and encryption. If the data to be transmitted is very large, it performs fragmentation. Okay, so each fragment can be of size 16 KB or less only. Okay, if the data is going to be larger than this, then we will be going in for fragmentation. Okay. So the first step in the SSL record layer protocol function is fragmentation. Okay, this each fragment is 16 KB or less. Now, once you have a fragment, it will go to calculate the MAC. Okay, how does it calculate the MAC? Each message is given a sequence number. Okay, the counter is when a connection is established by both sides, then both sides will initialize a sequence counter to 0. Okay, now this counter is incremented for each packet that is sent. The sequence number is not sent in the packet, okay, but it is used for MAC computation. So to calculate the MAC, it will concatenate the 64-bit sequence number and the fragment. Okay, sometimes the fragments may be compressed if compression is to be used, otherwise the fragment as such. Okay, the sequence number and the fragment together are concatenated and MAC is calculated. Okay, MAC will be appended to the fragment. Okay, next it will go to check the number of bytes that are there in the fragment plus MAC. Okay, it will check whether this is a multiple of the block size. If it is not a multiple of the block size, then a pad will be added so that the total number of bytes is a multiple of the block size. Okay, and this entire thing, that is fragment, MAC plus pad if necessary, will be added, will be encrypted. Okay, and now to this encrypted message, a prepended SSL record layer header will be added. A header will be added. Okay, now we know that this is coming from the application layer and this is going into the TCP layer. Okay, after the header is added, this record will be sent to the TCP layer for further processing. Now, what is there in the header? Okay, the header consists of a 1-byte content type field which identifies the higher layer protocol. Okay, you have a 1-byte content type field which tells whether it is a HTTP protocol that is being used or a FTP protocol, DNS protocol, whatever is the message, that will be indicated in this 1-byte field. Okay, next for version number, 2 bytes are allocated. Okay, and then you have the length field which indicates the fragment size in bytes. Okay, what is the actual fragment size that you have? This will be put in the length field. Okay, after adding all this, it is becoming a multiple of the block size. Okay, that is not put. What is the actual fragment size in bytes? That is put in the header. Okay, so the SSL record layer header consists of these 3 fields: the content type field, the version number, and the length field.